Recording. So welcome back everyone to the crypto lecture. And again, it's Thursday, so we're gonna stop a little bit earlier today again and around 1:45 and do the quiz. So let's get right back where we left off last time. All right. So we were here. So we were talking about greatest common divisors and had this little lemma which said that the greatest common divisor of two integers a and b can be written as a linear combination of a and b. So we can write a GCD of a and b as x times a plus y times b. And what we've seen so far is I've been talking about this set of all linear combinations of a and b, which we call an ideal. And I have shown that this set can just be for any numbers a and b, we find a number d such that I can be written as d times z. Right, so let me maybe put this stuff here on the what's happening? Why is this not? Okay, it seems something is not good. It seems like my iPad is frozen. Well, let's say the presentation is frozen. Let's try that again. No, I want pen. Does that work? That looks good. Okay. Okay. He doesn't let me erase stuff that I wrote last time. Good, so it's not frozen. That's fine. So first, I claimed that we have some we can write this this ideal I as d times z, where d is the smallest non-zero element in I. Right, so the inclusion from right to left is trivial. You can do that for an exercise, and from left to right, we just took ourselves a c in this ideal and just divided it by d. Right, we have division with remainder, so we get c is of the form q times d plus r for an r that is strictly smaller than d. But from that, we concluded that we can write r as c minus q times d. And if we write that out, that's a times something plus b times something else. So r is also in the ideal, but r is strictly smaller than d, right? And we said d is the smallest non-zero element in the ideal. So r must be 0. Which means, of course, that c is of the form q. Whoops. Therefore, we have c equals q times d, and that's, of course, in the ideal generated by d. Okay, so now I'm claim, and that's going to be a simple claim. D is the GCD of A comma B. So we had that D times Z equals A times Z plus B times Z, right? This is just what I wrote on the right side is just this I. From that is follows here on the left side, we have, of course, D is in D times Z, right? Because 1 is in Z, so D is on the left side. That means we can write D as A times X for some X in Z plus B times Y. Let's call them prime. But now both A and B are divided by the GCD of A and B, right? So write A equals GCD of AB times R, and B equals GCD of A comma B times T. And then we get that, well, D equals GCD of A comma B times Rx prime plus T Y prime, right? And that means GCD of A comma B divides D. So GCD of A comma B is a divisor of D. On the other hand, we have, of course, in the left side, we have that A is here in the right side, right? A times 1 plus B times 0. That means we can write A as D times, call it L, and B equals D times R. That means D divides A and D divides B. That means D is common divisor of A comma B. All right, so now I'm claiming we have everything. So I'm having here, I just wrote that D is a common divisor and that the GCD of A and B divides D. How can I conclude that that D must be equal to the GCD of A and B? I'm waiting. So I said D is a common divisor, and the greatest common divisor divides D. Why does that imply that D is equal to the greatest common divisor of A and B? Good, someone wrote something in the chat. If GCD divides D, then D is greater than the GCD. But since D is a common divisor, it must be the greatest divisor. Great, that's correct. So this is exactly the answer. So if D was strictly bigger than the GCD, then it would be a common divisor which is bigger than the GCD, which just violates the definition of GCD. We would have found a divisor which is bigger, a common divisor which is bigger than the GCD. So with that, we conclude that D equals GCD of A comma B, and the proof is done. All right, good. Let's quickly go over some corollaries without proof. We're not gonna prove these. They are rather simple consequences of this. And we're not, actually, I think we're not gonna use all of them, but let's quickly look into this. If C divides A times B and GCD of A comma C equals 1, then C must divide B. Therefore, if P is a prime and P divides A times B, then P divides A or P divides B. That's a simple corollary, but that's also something that we get directly out of the prime number theorem. Here's another corollary. If A divides N and B divides N and the GCD of A and B is 1, then A times B also divides N. So these two corollaries can be easily derived from this little lemma that we've just seen. Try it maybe yourself as an exercise. If not, you will find the solution or the way to do this in the book of Katz and Lindl in section 8.1. So book of Katz and Lindl, section 8.1, you will find the proofs of these corollaries. All right, now that we've talked about greatest common divisors, let's move on to modular arithmetic. So modular arithmetic is, as you might imagine, super important in crypto. We're all familiar with modular arithmetic modulo 2, but for the public key crypto part, we will have to do this modulo larger numbers. So let's quickly repeat some basic definitions or some basic concepts which should have been covered in your math lectures, right? Please, if this stuff was not covered in your math courses, someone please tell me, and we'll get in touch with the math department to align the contents of the lecture. So this is stuff that computer scientists should be should see in their math education. If it didn't, then someone please reach out to me, and we will reach out to the math department. So we say that A and B are congruent modulo n if there exists an integer q such that A equals B plus q times n. Right? This is the basic congruence relation modulo n. Okay, so here the conversion from Keynote to PowerPoint again messed up a little bit my notation. So here there's supposed to be white spaces in between there, but they were kind of ruined by the by this conversion. So for an integer a, we use the notation a modulo n to denote the remainder of a after division with n. So the remainder of a modulo n, or a modulo n, uniquely represents the congruence class or coset a plus n times z. Right? This is just the set of all integers of the form a plus n times z for some integer z. Right? Let's maybe quickly draw this, how this looks. So this set, if you have 0 here, and maybe n here, then this, and your, let's say your a is here, then this set a plus n times, so let's say minus n, a plus minus 2n, right? A plus, let's use a different color for this, maybe. A plus n times c is this blue set, and so forth, right? This is basically, yeah, a set where we, where all these elements a plus n times c are included in this set, right? This is our a plus n times z. Good. So, but now you see there's infinitely many elements in this set. And when we want to represent this set, we just take the smallest positive element in this set to represent it, and that is just a modulo n, right? Let's say if a was here, right? Let's maybe erase this. Then we can make a modulo n is here. This is just the element in this set a plus n times c, which is positive and closest, or non-negative and closest to 0. All right. So clearly we can identify, or we can represent this entire set A plus n times z with A modulo n. Right? If I know what A modulo n is, I know what the entire set is. So now, whoops, we, I don't like this. There's white spaces here. We define the set Zn, which is the set of all congruence classes modulo n. Okay, so we said A mod n represents a congruence class, and Zn is now the set of all congruence classes. And of course, let's go one further. It holds that Cn corresponds, if we just look at the representatives, to the set 0 and so forth until n minus 1, right? So we know that Zn is of size n minus 1. And we can even easily compute, of course, with these representatives. Just take two representatives from this set, perform, let's say, addition or multiplication, and reduce mod n. So we define addition and multiplication on Zn as this is really annoying. A mod n, or the sum of two congruence classes, is just the congruence class of the sum, right? A mod n plus B mod n corresponds to A plus B mod n. And the same for the product. And let's quickly look at an example of this. Right? Let's say I just took this example from the book. I mean, that's really just a very simple thing. Let's say I wanted to compute this number here, 1 million and so forth, times 190,301 modulo 100. What is that? Well, 100 is a lot smaller than these two numbers, so it would be silly to first compute the product of these two numbers, right? Let's first reduce these numbers modulo 100 and then compute the product, right? This is is congruent to, by the way, I should maybe also write that here. This is congruent as a residue class, or as a congruence class. It's not equal, but congruent to. Good. So this is the same as 1,093,028 modulo 100 times 190,301 modulo 100. Then again, since we form congruence classes, I again need to reduce modulo 100. But what's that? So this is the same as, I'm conveniently reducing modulo 100, right? That means I can just drop anything from the second digit onward. So this is 28, and this is 1. So 28 times 1 mod 100. This is just 28, right? Really, when I'm computing modular arithmetic, the way we do it is we first reduce, then do our computation on the reduced values, and then reduce again. That's how we compute on these representatives. But there was a question, can you maybe explain why we need to add the last mod 100 at the end there? You don't need to add it. I mean, I'm just writing, this is congruent. This last modulo 100 doesn't do anything, right? So what we're doing here is we are computing on these representatives, and we just have to make sure that if we after some operation would end up outside of this this set of representatives 0 to n-1, that we map back with a modulo n operation. Good. So there's another question. How are 2 mod and 1 mol operation more efficient than 1 mod and 1 mol? So the thing is, oftentimes, not always, right? But oftentimes, as for instance here, computing modulo can be super cheap. Not always, right? A modulo operation can be expensive as a multiplication, but the thing is, since we're here reducing modulo 100, whenever you're reducing modulo, let's say in base 10, modulo a power of 10, that is super easy. You just drop positions. And the same is true, of course, when you have a base 2 representation and reduce modulo 2 to the n or something. And furthermore, this here is actually the way I did this calculation would actually be more efficient even if I wasn't reducing modulo 100, but modulo something else. The reason is that if you look at this, I mean, we're not computing with bit numbers, but with base 10 numbers. So here, this multiplication is a multiplication of a 7 digits number times a 6-digit number, right? And let's say I'm reducing these if I wasn't reducing these modulo 100, but reducing them modulo a 3 or 4-digit number, then it's even asymptotically cheaper to first reduce the modulo the 4-digit number than doing the multiplication, getting a super large value, and then reducing it modulo this 4-digit number. So the reason in some sense for this is that we don't have linear time algorithms in the bit length to do multiplications, right? Multiplications of long numbers are more costly than first reductions by somewhat shorter numbers and then multiplication of short numbers, right? So this multiplication is a costly operation, and you want to do it with as short inputs as possible. Okay. Good. Now, let's talk about multiplicative inverses. So the okay, so this should have built up, but clearly in the integers, the only number with multiplicative inverse is plus minus 1, right? Plus minus 1 have multiplicative inverse because every time it's just in itself. Clearly, 0 has no multiplicative inverse, and all other numbers in Z, their multiplicative inverses are in Q. That's how sort of we define Q. Q is the closure over all multiplicative inverses of Z. it's the additive or the Z closure of all multiplicative inverses in Z. So good. That is the multiplicative structure of Z and Q is simple, but now we have this new structure Zn. We can do additions and multiplications on Zn. And we may ask, just as I asked right now, which elements in Zn have multiplicative inverses in Zn? Right? We know for Z, this is just plus minus 1. For Q, this is everything but 0. How about this, this structure Zn, these integers modulo n? Which of these guys have a multiplicative inverse? And that leads us to the following lemma. So again, let a and b integers, where a is non-zero. Let's say a is non-zero. I wouldn't even have to require that, and n is greater or equal than 2. Then a modulo n has a multiplicative inverse in Zn if and only if GCD of a comma n equals 1. Right? So this gives us a very nice characterization of which elements in Zn have multiplicative inverses. So GCDs can be computed easily. By the way, I also wanted to let's do that example afterwards. How we will use this to compute multiplicative inverses, but let's first go into the proof of this, which is rather simple. So how are we gonna prove this? Let's which direction do we do first? So let's say GCD, the important direction of a comma n equals 1. Okay. How can I deduce from that a has a multiplicative inverse of modulo n? Well, we've just seen this lemma earlier today. Let's call it lemma 1. That this means we have x and y such that a times x plus b times n equals 1. What does that mean? What can we deduce from that? When over the integers, it holds a times x plus b times n equals 1. Someone wrote b is inverse of a mod n, and someone else wrote x is the inverse. So who's in favor of b and who's in favor of a? Sorry, of x. Okay, it seems like we have a consensus for x, and this is correct. We have a times x plus b times n modulo n, right? Is of course a times x mod n plus b congruent b times n mod n, but b times n mod n, that is just 0, right? And you know that a times x plus b times n, this is just 1. So we get that 1 is congruent to a times x modulo n. And that means x is a multiplicative inverse of A. So in the other direction, what if we have a multiplicative inverse? So what if A times X congruent 1 modulo N? Well, so this was this direction, and in the other direction we have A times X congruent 1 modulo N, but again this means 1 equals A times X plus let's call it N times, sorry, no one told me that why did I use this B there. This shouldn't be B, this should be Y. I should have written Y here. So here, this is Y. Tell me when I do these blunders. N times Y, just from the definition of congruence. And this now means that if we go back, exactly, once we have this equation here, it holds that Z equals A times Z plus N times Z. Because I mean, A is in Z, this is clear, N is in Z, but from this equation above here, we have 1 is of the form A times X plus N times Y, and therefore every element in Z can be written of the form A times some integer plus N times some integer. So, what I want to say, this now means that, yeah, do I even have to write this to conclude that the GCD must be 1? Yeah, exactly. So, no, I don't need this second line here. From this, it immediately follows that the GCD of A comma N equals 1, right? Because if the GCD of A and N was anything bigger than 1, then every linear combination of A and B would be a multiple of their GCD. You couldn't reach 1 if that GCD was not equals 1. Okay, good. This is this. Let's go for an example. So far, I haven't told you how to compute the greatest common divisor. How do I compute the greatest common divisor? Euclid's algorithm. That's great. But next question. I'm using already here that I can express the GCD as A times X plus Y times or B times Y. How can I find these X and Y, right? Whoops. So, yeah. I have here that I get that such for every AB there exist X and Y such that GCD can be written as a linear combination. Oh, and someone wrote already the answer. We can find that via the extended Euclidean algorithm. And just for fun, let's do that real quick. Let's go over the extended Euclidean algorithm, right? Let's say we would like to find 21 inverse modulo, let's say 29. Okay, we compute 21 inverse in Z29. How can I find this? How can I find which of these 29 values, or should be one of 28, is the inverse of 21? Well, for such small numbers, right? Sometimes the most efficient thing is just to try all of them. To enumerate all these elements and try which one is the inverse. But if instead of modulo 21 we reduced modulo 1024-bit number, this wouldn't be that easy. So the way we do this is via the extended Euclidean algorithm, or the so-called ELBA algorithm, the Euclid-Lagrange-Berlekamp algorithm. So let's look quickly at GCD. I hope I'm not boring you, of 29 and 21. Right, so what we do is, of course, we start with the first step of Euclid's algorithm. We do a division with rest. We divide the larger number with the smaller one. So 29 is just 1 times 21 plus 8. Okay, that's the first step. But now the ELBA algorithm keeps linear combination in its memory, right? So now we know that we can express 8 as a linear combination 1 times 29 minus 1 times 28. We just remember that we can express 8 or this intermediate result as a linear combination of the two inputs. Oh, 28, thank you. Yeah, it should be 21. Why am I writing 28 here? 21, thank you. So let's do the second step of Euclid's algorithm. So there we have 21 divided by 8. Well, this is just 2 times 8, 16 plus 5. All right, that means we can express 5 as 1 times 21 minus 2 times 8. Okay, but now here we also have this 8 on this side here. So what we're going to do is we just plug in this linear combination that we computed in the last step. So this is 1 times 21 minus 2 times 29 plus 2 times 21. Right? 1 times 21 plus 2 times 21 now gives us 3 times 21 minus 2 times 29. All right, so we again have written this intermediate result, the 5, as a linear combination of 21 and 29. Let's proceed. Next step of the basic Euclidean algorithm. We can write 8 as 1 times 5 plus 3, or in other words, 3 equals 1 times 8 minus 1 times 5. And now let's just plug in the linear combination that we got for 8 and for 5. So this is 1 times 29 minus 1 times 21 minus 3 times 21. 3 times 21 plus 2 times 29. And what is this? Well, 1 times 29 plus 2 times 29 is 3 times 29 minus 4 times 21. Good. Let's continue. Here we continue with Euclid's algorithm and compute the divide 5 by 3. So 5 is 1 times 3 plus 2. So we get 2 equals 1 times 5 minus 1 times 3. But now we have already these expressions of 5 and 3 as linear combinations of 29 and 21, right? So 1 times, this is not 15, 1 times 5. So let's write this 3 times 21 minus 2 times 29 minus 3 times 29 plus 4 times 21. This is just 3 plus 4 is 7 times 21 minus 5 times 29. Good, we're almost done. Of course, when we do a division with the rest, 3 divided by 2 is 1 times 2 plus 1. And now we're done, right? It can't go smaller than 1. If we ended up with anything else, we would have to do an additional step to see that the remainder is 0. But now we have 1 is 1 times 3 minus 1 times 2. And now let's again use these expressions that we found here. This is just 3 times 29 minus 4 times 21 and minus 7 times 21 plus 5 times 29. So makes altogether, where are we? 3 times 29, 8 times 29. Good. We have 8 times 29 minus 11 times 21. And there we go. We have minus 11 times 21 plus 8 times 29 equals 1. Therefore, 21 inverse modulo 29 is minus 11 inverse modulo 29. What's minus 11 modulo 29? $18. That's correct. 29 minus 11 is 18. And we're done. That's how it goes. That's how we compute even by hand, right? I didn't use any calculator or anything for this. This is how I compute modular inverses even by hand. And in fact, this is also how computers do it, right? The ELBA algorithm just keeps track of the linear relations that it already has yeah, builds them up, so to speak, when we proceed through Euclid's algorithm. Okay, good. And that's it for this part. Keep. Save copy, just to make sure. Okay, and now let's move on. We have a little bit more number theory to do. Good. Wow, but the time is already quite progressed. I'm making slower progress than expected, but yeah, we should finish up the preparatory number theory stuff in the next lecture, then and then proceed to the public key crypto stuff. Okay, so rings and fields. The integers that we know and love with addition and multiplication are commonly referred to as a ring, right? Structures in which we can add elements, subtract, and also multiply, but in general don't have multiplicative inverses. Those structures we call rings. And the prime example for a ring is, of course, the ring of integers, Z, right? Addition and multiplication gives you a ring. Now, we know that if P is a prime, then it holds for every integer between 0 and P that the GCD of X and P is 1. That's what primes are. They don't have non-trivial divisors. So, since we've seen that every element in Zn with we've just seen that every element in Zn with GCD of X and N equals 1 has a multiplicative inverse. That means in Zp, every element except 0 has a multiplicative inverse. Okay, and such structures we call fields. So in a field, every element except for 0 has a multiplicative inverse. Now, of course, 0 cannot have a multiplicative inverse. You cannot multiply 0 with anything and expect it to be 1, because multiplying with 0 always gives you 0. So there's a question, have we seen a proof for the third bullet point already? Yes, we have basically just in the last lecture, if remember, let's use some other color. If GCD of A comma P equals 1, then A has multiplicative inverse modulo P. Okay, but now it's from up here, we know that every or let's not call it A, let's call it X, like up there. Now we know that every X, every non-zero X smaller than Z has a GCD of 1 with P, and therefore it has a multiplicative inverse. Good. Of course, you've seen other fields in your math classes already. The first field people get to know are the rational numbers, Q. Then you get to see the real numbers, R, and also the complex numbers, C. So those are typically the fields that you love and work with in calculus classes, right? Those are what analysis and calculus is about. Okay, now, if n is a composite number, so not a prime number, then of course we've seen that Zn is a ring, but it's not a field. Okay, so I'm claiming there are elements that have that don't have multiplicative inverses. So, but the question is, for a simple n, can we relate Cn to some fields, right? Can we sort of express this ring in terms of these simple objects that are fields, right? Think of fields as simple objects, because everything has an inverse. There are no troublemakers, right? Think all the elements in Zp, except for 0, right? 0 is maybe a troublemaker, but all the others have multiplicative inverses. So by the way, let's say n is composite, something like n equals 15 is 5 times 3. Can someone tell me an element in Z15 that does not have an inverse? 3, 5. That's good. Or why don't they have inverses? How can we? By the way, are these all, or are there more elements that don't have inverses? Good. Yeah, you're writing it. The GCD is not equal. GCD is not equal 1. But of course, we have a few more elements, right? It's of course 5, 10. I mean, 15 is 0 modulo 15. But then we have 3, 6, 9, and 12. Those guys don't have inverses because they have a non-trivial GCD with n. Okay. But now I asked, can we somehow, if n is simple enough, something like 15, 5 times 3, can we relate Zn to some fields? And surprise, surprise, I'm going to talk about the Chinese remainder theorem. So what does this say? It says the following. Let's take two prime numbers, p and q, that are different. And let's set n equals to p times q, something like 15 that we just had. Then it says that Zn is isomorphic to Zp times Zq, to the direct product of Zp and Zq. That means, what does it mean to be isomorphic? There exists an isomorphism from Zn to Zp times Zq. I'm going to explain a little bit more what it means for something to be an isomorphism. But this says that if you have a mapping which preserves structure, this is the homomorphism part of isomorphism, you have a mapping which preserves structure, which goes from Zn to Zp times Zq, and you can go backwards, right? Then basically this means if you have your Zn here and Zp times Zq here, well, this means you can translate from Zn to Zp times Zq via phi and translate back to Zn via phi inverse. That means someone is asking what is meant by structure, and the structure that I'm talking about here is the ring structure. Okay, what does that mean? Let's say you have x plus y here. You want to compute x plus y, but let's say you say computing x plus y is a bummer in Zn. So what you can do first is translate to Zp times Zq via, let's say you either want to, let's compress that a little bit, either want to compute the sum or the product, right? You can first map x to phi of x and y to phi of y. And now instead of doing the computation on the left side, you can do it on the right side. And the nice thing now is, how do I compute additions in Zp times Zq, right? So we have a direct product. So we do computations independently in the two components. I'm gonna talk about this, how this works in a moment. But then you can compute, let's say, phi of x plus times y, and then you can again move back. You can again move back with, psi inverse, and get the same result, right? That's what it means to be an isomorphism. You can choose to either do your calculation in Zn or in Zp times Zq, right? It's not just that phi is a bijective mapping that identifies each element on the left side with something on the right side. No, it also preserves addition and multiplication. That's the homomorphism part. Good. So, but of course, the operations on Zp times Zq are component wise, right? E.g., let's say a comma b times x comma y is just a times x comma b times y. That's how we compute in such a direct product, and that's like super nice, right? What the Chinese remainder theorem does is it takes this somewhat obscure structure Zn and breaks it down into very nice and gentle structures. Zp and Zq, they're both fields, right? And so instead of computing in my ring, I'm computing in parallel into different rings. That's what the Chinese remainder theorem says. By the way, does anyone in the audience know why this is called the Chinese remainder theorem? Just for curiosity. What does this have to do with China? Someone should know. Counting on one person to know. Because someone asked because of the abacus. I don't think so. Or someone says I think it was invented by a Chinese mathematician. We don't know the name of the inventor. So I mean, why we generally referred this to this as the Chinese remainder theorem is because we know that in ancient China, astronomers used this theorem to compute alignments of planets. Right? Let's say, I mean, I could go much deeper into this, but probably I won't have time. You have a planet with a period P and a planet with a period Q, and now you want to find out at which day those two planets are in alignment. You can actually use the constructive version of the Chinese remainder theorem to compute that. So the origins of this are actually astronomy, right? Astronomy in ancient China. But let's quickly go into the proof, which is not that hard. Now, what is my my mapping psi from Zn to Zp times Zq. So let's say I'm having an x in Zn. What do I map it to? Proposals. What could I map this x to? What's the canonical thing you might do? Yeah, good. Someone in the chat wrote the answer. I'm computing x modulo p, comma x modulo q, right? And the first thing you need to check, which I'm not going to do now because this is really a simple routine calculation. Check psi is well defined, right? If you have two inputs, x and and y such that x is congruent y modulo n. This means x equals y plus q times n, but that means x modulo p is y plus q times n modulo p, which is sort of y modulo p plus q times n mod p. And since p is a divisor of n, this is of course 0. So this function is well defined. The second thing you need to check is that psi is a homomorphism, right? But this is also easy because we know reduction mod p is a homomorphism and reduction mod q. So this is easy. What else do I have to check? So now I've established the function psi is well defined. The function psi is a homomorphism. What do I owe you still? What do I have to show you still? I mean, you just have to go back to the last slide. What did I say on the last slide? Aha. Psi must be invertible. So we need an inverse function. I think I still have an extra slide here. Let's say x prime comma y prime element, well, let's call it AB. AB is in ZP times ZQ. In other words, A element ZP, B element ZQ, right? Find x, so let's say psi is invertible. Find x such that x in Zn such that psi of x equals a comma b. Okay, that's what we have to show. And how can we do this? Well, we're not starting from 0. The first thing that we do is, so even though A is in ZP and B is in ZQ, what we're going to do is we just lift, I'm calling this lifting, A comma B to Z, right? Let's say interpret as integers. So let me be even more expressive about that. Forget that we need to do modular reductions, right? Forget about modular reductions for a moment. Okay, so now I'm telling you one thing, P comma Q R prime. What does that mean about the GCD of P and Q? It's 1. Yes, someone wrote it's 1. That means GCD of P comma Q equals 1, right? And for that, we know we have P times some integer x plus Q times some integer y equals 1. So in other words, x is the inverse of P modulo Q and y is the inverse of Q mod x. So x is P inverse mod Q, and y is Q inverse mod P. Okay, so and now I mean, there's probably a very nice way to motivate this, but now I'm just telling you what I'm going to do. I'm going to set x equal to let's say A, and recall that I'm forgetting that A is in ZP. I'm just lifting it to Z times Q times Y plus B times P times X. Okay, that's what I'm computing in, well, let's call it X prime in Z, and I'm just setting X equals X prime modulo N. So all we have to do now is to check whether psi of X equals A comma B. Let's do that. Psi of X is, well, here we have A times Q times Y plus B times P times X modulo P, and here we have this A times Q times Y plus B times P times X modulo Q, and I'm again running out of space. But if you look at this here, since we're reducing modulo Q, modulo P, this is 0. And here on that side, we know that Y is Q inverse modulo P. So this is 1, right? And here again, we know this is 0, and P times X modulo Q, this is 1. So we're getting this is A comma B. A little bit tight, a little bit out of space, but we are done. So I can express the inverse of this A and B just as a linear combination of A and B over say the integers, or actually modulo N. Okay. This is was the proof of the Chinese remainder theorem, and this proof is actually constructive, right? I've told you actually how to do this, how to invert this this homomorphism. I haven't just told you it's possible to invert it. No, I've actually showed you a simple formula how to invert, right? So first find X and Y such that P times X plus Q times Y equals 1. And then this is how you actually invert it. Shouldn't it be phi of X prime equal, I mean, phi of X and phi of X prime, in the end, it's the same thing, right? If you add a multiple of N and reduce it mod P, this multiple of N becomes 0. So yeah, maybe this whole X prime business, not that important. So, but that said, let's quickly look at an example, right? So for our Chinese remainder theorem, let's say P equals 5, Q equals 11. And let's say we want to do the following. We're looking for an X, looking for X in, let's say, Z55, such that X modulo 5 equal 3 and X modulo 11 equals 2. Okay, so how are we gonna do this? Well, I told you, so here's how I like to do that if I have to do it in my head. Going back to this, basically X is P inverse modulo Q and Y is Q inverse modulo P. So let's look for these things. Whoa, whoa, too fast. So what is 5 inverse modulo 11? So now we're just we're not throwing the ELBA algorithm as a how do you call that? The A already stands for algorithm in ELBA, but we're not throwing ELBA at this, but we're just doing this in our head or quickly by trial and error. Okay, you're super fast. I was going to ask, what do I have to multiply 5 with to get 1 modulo 11? What's the inverse of 5? And yes, 5 times 9 is 45, which modulo 11 is 1. So this is 9. On the other hand, what is 11 inverse modulo 5? Well, 11 modulo 5 is just 1. This is also just 1, right? 11 modulo 5 is 1, and the inverse of 1 is 1. So let's do this. Now our X is first we have this 3, right? From here, 3 times exactly 11 times 1, right? This is Q, and this is Q inverse mod P plus 2 times 5. This is P, or let me use a different symbol. These look like fractions. They shouldn't look like fractions. Times 9, and this is P inverse mod Q. And now we just need to calculate, right? 3 times 11 is 33 plus 90, and that's 123. And now let's reduce modulo 55, right? Our n is 55. So, of course, modulo 55, so the nearest multiple is 110. This is congruent 13 modulo 55. Good. And that's how we do Chinese remaindering. I think, yeah, I wanted to get a little bit further today, but I'm not gonna get there. So next thing, of course, that we talk about are groups. But let me maybe take the opportunity to ask you, are there any questions regarding this? I mean, of course, we will at some point have exercises where you have to compute CRDs and GCDs and whatnot. Those are just too good. Those just make too good exercises not to use them as such. So, does anyone have a question? If not, probably let me just go into the Moodle. I think it's again set to start a little bit later, namely at 50. Whoops, log in. So quick test 7, yes, it starts. Zip. Go to activity. time at 13:45. Okay, which is pretty much now, right? So since I'm pretty much done, I'm activating the quick test now, and yeah, seems like no one has a question. So yeah, have fun with the test, and I would say see you next Tuesday. Thanks, everyone.